This is the second part of the atomic and nuclear physics. We'll do the first part, which is about radioactive decay, alpha, beta and gamma radiation. And we'll look at the ionizing properties of alpha, beta and gamma, and then the biological effects. Describe the phenomenon of radioactive decay. Radioactive decay is a natural process. You need to know of the anti-neutrino which is produced in beta decay. So, radioactive decay is when you have an unstable nucleus which undergoes a nuclear change. You need to know that it's a random process, it can't be predicted, and this unstable nucleus becomes a more stable nucleus. Also, the decay rate decays exponentially, which means in a given period of time it will halve, and in the same period of time it will halve again. This is an exponential decay. It can be the release of alpha particles or beta particles and an antineutrino, or it can be a gamma radiation. So let's look at alpha decay. You'll have to forgive this clumsy way of annotating this. This is the atomic mass, this is the atomic number. The atomic mass is reduced by 4 because it loses 4 particles. There are 2 protons and 2 neutrons in the helium nucleus, so 4. And the atomic number reduces by 2, so this is where there's 2. What you should know is that the number of nucleons should add up. A is equal to A minus 4 plus 4. Z minus 2 plus 2 must equal Z. Sometimes this is written as an alpha sign. Beta decay. What we have here, notice that the atomic number, the atomic mass value stays the same. The atomic number increases by 1. This is the beta particle, and we have what's called an antineutrino here. Notice that the atomic mass before is equal to the atomic mass afterwards, and the atomic number before, the sum of the atomic numbers will be the same. This antineutrino is basically a translation of it, means the little neutral one. For years and years these were not able to be seen, they were not detected, they were neutral and they were very small. So we basically, when we're looking at this, you check to make sure that the A is conserved and Z is conserved and charge is conserved. So let's look at nuclide notation. This is a symbol for an element. We have one value here, which is going to be atomic mass, and another value here, which is the atomic number. A is equal to the sum of protons and neutrons. Z is atomic number, which is thus the number of protons. The nucleus decays and releases an alpha particle, or a helium nucleus, and it means that the nucleus will become lighter by the mass of an alpha particle. So therefore it loses 2 protons and 2 neutrons. So the atomic number reduces by 2, the atomic mass reduces by 4. And here we have an example. What happens here? We have A and Z. This is atomic mass, atomic number. We have alpha decay. So that's going to be 4 and 2. But what's going to happen to this number, A, is going to reduce by 4. And this number is going to reduce by 2. However, this is not correct. The atomic number of this element X is Z. The atomic number of this element is Z minus 2. So therefore it cannot be the same element. So it must be another different element. So it decays to another element. And a real example would be that thorium 90, which is thorium-232, emits an alpha particle, which is 42, and this will come down by a number of 4, this will come down by 2. So 232 minus 4 becomes 228, 90 minus 2 becomes 88. Of course it's not thorium anymore, this is now radium, because the number of protons is different. Now beta particle, beta decay. Now we look at beta decay. Beta decay is when it emits a fast-moving electron from the nucleus. Now, we have a problem here. You do not get any new electrons in the nucleus. So how is it possible that an electron can come from the nucleus? Because this is nuclear decay. So what happens in this process is that a neutron, the nucleus is unstable, so a neutron will decay. It will decay into a proton and an electron, and one of these things called an antineutrino. We start off with zero charge. The proton is positive charge, and the electron is negative charge, so they cancel out. So we start with neutral charge, we end up with neutral charge. This has no charge. What it means also is that the atomic mass will stay the same. However, the atomic number will increase by 1, because now we have an extra proton in place of the neutron. So what we could have here is that we know here that the atomic mass is going to be the same. We also know that Z is going to increase by 1. So the atomic mass is the same, and this one increases because there's a neutron which turns into a proton, so the proton number increases by 1. Of course, this cannot be X anymore because it's a new element, it has a new atomic number. So we call this Y, plus the antineutrino. Notice that the atomic mass is unchanged. Another example, here we have 228, 89 of actinium. We know this is beta decay. The atomic mass is going to stay the same. The atomic number will increase by 1 because the neutron turns into a proton. You will get one more proton, the atomic number increases by 1. So this stays the same. This increases by 1. Notice that we put -1 here because it has a negative charge, and when you add this to this you end up with 89, so this value is balanced. So now this is thorium. Different element. This has an atomic number of 90, this has an atomic number of 89, a different element. Another example, we start with radium. So you have to decide what will happen here. Well, a neutron turns into a proton. The number of nucleons will stay the same. So here we will have 228. The neutron turns into the proton. We end up with one extra proton, so this goes from 88 to 89. And this becomes actinium. Uranium-238, for example, undergoes alpha decay. Then what's left undergoes beta decay, then beta decay, then alpha decay. So as this happens, it produces a new element. This is uranium-238, becomes 234. Now this is going to have the same mass, but a different element. Same mass, but different element. Then we lose 4 units, and lose another 4. There's another 4, and so on. Now this is a decay series. Describe the properties of alpha and beta particles and gamma radiation. An alpha particle is a fast-moving helium nucleus which comes from the nucleus of an atom. It's heavy, it's very highly ionizing and has a charge of +2. Beta particle is a fast-moving electron, is small, negative charge. Gamma is radiation from the electromagnetic spectrum. It has no charge and it has no mass and is not considered a particle. This shows how penetrating these different radiations are. Alpha particle does not penetrate very much. It ionizes very quickly, so it gets absorbed. Beta particle ionizes a bit less, so it will go through paper, whereas alpha particle will not go through paper, but it will not go through aluminium. Gamma will go through paper, aluminium, and it must have a large, thick amount of lead to be stopped. Here we have another graphic to show this. Alpha, beta, gamma. Only beta, gamma get through the paper. Only gamma gets through the metal, and with a thick lead wall, gamma can be stopped. The ionizing properties. Alpha, beta, gamma have enough energy that they remove electrons from atoms when they pass, so all three are ionizing. Now, alpha particles are very highly ionizing, and that is why they don't travel very far, because their energy is absorbed very quickly, and therefore they're not able to penetrate very deeply into a material. Beta particles, they're also ionizing, but the energy is absorbed quickly, but not as quickly as alpha particles. Therefore, they're more penetrating. Gamma radiation is not very ionizing, so it's able to travel some considerable distance before the energy is absorbed. Biological effects of ionizing radiation. Ionizing radiation, since it ionizes, can disturb and change the DNA structure in nuclei and can cause cancers. And if you have a cancer, that can be treated in short term by using radiation therapy to damage this cancer cell. And what that causes reddening of the skin, loss of hair, and also radiation burns. In the long term, it can cause more cancer and genetic mutations.